Together with the EuMIC team, composed by AndreiaCathelin from STMicroelectronics as the co-chair, Jean-Christophe Nalatambi from the University of Limoges as TPC chair, and Joaquin Portilla from the University of the Basque Country TPC chair. We are very pleased to welcome you in Paris, and we have 43 EuMIC delegates. So I will talk about first the conference events. So we are very pleased to have 3 plenary talks, 2 during the opening session. We first will have a talk given by Chris Rudell on modern intelligent system. Then just after a talk given by AndreiaCathelin from STMicroelectronics on FD-SOI and IoT application. And tomorrow, during the closing session, we will have a talk given by Valeria Di Giacomo Brunel from UMS on error front-end technologies and integration. As I talk about the closing session, it will be tomorrow at the end of afternoon. So just after the first plenary talk, we will have the traditional EuMIC Foundry session. It will be chaired by Eric Leclerc from UMS, and the principle is a panel discussion with leader companies and foundry representatives. So we will have a representative from WIN, MECOM, Global Foundry, IHP, STMicroelectronics, and UMS. And this discussion will be on how do you see the needs and demands for foundries developing, and how do you plan to meet them. After the foundry session, there is an award ceremony chaired by Olivier Lafont, European Microwave Week TPC co-chair and award chair. We have 4 prizes. The first prizes is the EuMIC prizes, sponsored by MECOM. We have then 2 Young Engineer prizes, sponsored by Soitec and Corvo. And we have also the Tom Brazil Fellowship Award, sponsored by the Gas Association. Then we'll finish the session by closing remarks and an invitation to the 2025 edition by Marion Matters-Kammerer, the EuMIC 2025 chair. We have also some social events during the conference. So tonight you will have the EuMIC get-together. It is a finger food cocktail when you can discuss and meet colleagues and friends. It is at 6:30 and it is free for EuMIC delegates, but you need a ticket that you will pick up at the registration desk. But everybody is invited to this get-together meeting, every EuMIC delegates, of course. And this is sponsored by MCAD, Engineering, the Gas Association, and UMS. You are also invited to the UMW welcome reception. It will be tonight, just after the closing session. If we look in the EuMIC2024 in figures, so we have 643 registrants. It is the best attendance ever for EuMIC conference. Regarding to, Regarding to the submission, we had 179 papers, and you have in the table the repartition in the different theme of the conference. We called it subcommittees. So you have modeling, simulation device, you have RF and microwave device and technology, integrated PAs, millimeter wave ICs, microwave and millimeter wave system and application, and special sessions. And among the 175 papers, the TPC members worked and selected 118 papers. It leads to an acceptance rate of roughly 66%. It is close to the past edition last year in Berlin. So we have 93 oral and 25 posters, and we have 24 sessions and 6 sessions in parallel. We have 1 joint poster session with UMC, and we have also 5 invited industrial keynotes. So if you have a look also on other figure, this is a repartition of submitted papers and accepted papers by country. So you see that the German community sent a lot of paper and have also a lot of accepted paper, of course. And then there is a French community, but you know that EuMIC is an international conference. So the third one is in the United States, and then China, Japan, Sweden, and so on. We have roughly 30 countries represented here. So it is not a competition at all, but just to see where the papers come from. Regarding to EuMIC, we have 5 this year industrial keynotes. The 2 first were given earlier this morning in the first slot of sessions. The first one was Charles-Edouard Kakou from MACOM, discussion about differentiated technologies for next generation radar and mobile communication. The second one was given by Wissam Sahab from ANCAD Engineering on the methods for measuring and modeling GaN transistors and estimating PA performances. And after the opening session, you can follow the talk of Soitec given by Christophe Malville on engineer substrates and connectivity. The speaker, Sanke Wering from Bosch on radar socks for multi-bit phase shifter in modern CMOS technologies. And the last one speaker tomorrow afternoon will be given by Baudouin Martineau from CEA Leti on millimeter wave circuit design in CMOS, design and layout consideration. So in EuMIC, we have also a workshop organized. It was yesterday, so we had 4 workshops on terahertz device circuit and systems, on technologies and circuit for RF modules, on design characterization and integration for active phase array, and on ultra-wideband efficient PA. So to organize EuMIC, we need a lot of involved people, and so I will address a warm thanks to all the European microwave team, especially Professor Guillaume Ducournau just here. Thank you. I will also thank all the EuMIC reviewers, the TPC members, and the session chairs, the student helpers, the authors, of course, the attendees, you, the sponsors, the European Microwave Association, the workshop organizers, the committee prize members, all the technicians in the room, and the previous team for their valuable advices. Thank you very much, and enjoy the EuMIC 2024 in Paris. Okay, so I will follow by the first plenary talk. It will be given by Chris Rudell from the University of Washington. So Chris received degrees in electrical engineering for the University of Michigan, and then a master's degree and PhD degree from UC Berkeley. After his PhD, he works as a RF IC designer at Barcana Wireless, which is now Qualcomm, and Intel Corporation. In 2009, he joined the University of Washington, Seattle, where he is now professor in electrical and computer engineering. Chris received a lot of distinction in conference, among them twice being co-recipient of the Best Paper Award at ISSCC. Chris is involved in various IEEE solid-state circuit conferences. Is part of the TPC of SCIRC and ISSCC. He is involved in the RFIC steering committee since you were the general chair of RFIC in 2013. And Chris, it's my pleasure to welcome you for this opening session. So you have roughly 30-35 minutes, not more.
Not more.
And then after a discussion with the audience. Okay?
Okay.
Thank you.
All right. Well, of course, I'd like to begin by thanking Natalie and the entire committee at the European Microwave Conference for this invitation to speak here today. The area, that I do a lot of research in, and it's an area of interest, for about the last 10 years, particularly in the wireless community, is the topic of, how to address self-interference, particularly in wireless systems. But in general, I think this is a great problem to focus on for many technical reasons, both on the circuit side, the architecture side of the chip, and even on the system side, and now some emerging areas like AI and the use of AI in these type of systems. So I broadly classify it as not just like a full duplex radio, but just self-interference in general. And so what I'm really talking about is there's really 2 things that are going on here, 2 trends I'd like to say. One trend is that we're always increasingly integrating more and more things onto the chip, right? So the opportunity and the isolation between various components is decreasing. and the opportunity for some signal that we're generating to interfere with another signal that we want. In the case of a wireless receiver, that's the received signal. That possibility is increasing significantly because the isolation is dropping. Now, there are some applications that are emerging, which are very interesting in my opinion, and then there are other applications where this problem has existed for decades, but they've come up with system solutions. One, for example, is time duplexing both this interfering signal with this desired signal. What we'd like to do is have both signals operate at the same time and some way mitigate this unwanted signal in our system. And so, we just show the general case here for some system and a chip, transmitting, receiving, and the media could be anything, wireless, wireline, and even bio applications. And so specifically, so what I'd like to do in today's talk is just briefly look at some commonly found self-interference systems applications that I actually think are very interesting, one of which I worked on. Then, of course, it's a wireless conference, so we'll focus on the topic of radios and in-band full duplex communication, which I think is a great problem, technical problem to work on for many reasons, even if you don't believe that full duplex radios will actually come to light in the future, manufactured, in mass and used in 6G and 5G applications. I do, but even if you didn't believe that, it's a great problem, and I hope to give you an appreciation of that by the end of this talk. So the first application that I think is actually pretty cool is the issue of self-interference in neural interfaces. Specifically, a lot of the work that we've done at the University of Washington, we have a very strong medical school, so we collaborate together. We'd like to do stimulation either on the surface of the brain or somewhere in the central nervous system while we're sensing or recording neural activity. And this is classified as one of those problems that has been around for decades. Trying to sense neural signals in the presence of strong stimulation signals when we're trying to stimulate nerve tissue and simultaneously listen through sensing. So the stimulation is going to, the electronics is going to overwhelm the sense electronics. So that's been a classic problem. They use something called blanking. We would call it TDD or TDMA. So it's time domain duplex. But unfortunately, there are, there's some interesting scientific questions that we would like to be able to study. What happens with what they call close neural circuits, so with very short latency, and where we stimulate and we sense very close physically and see what neural activity takes place. The problem with blanking is that after you're finished blanking, that neural activity has already died away, and when you turn on the sense recording. So we'd like to have some distortion-free way of sensing the neural activity through the entire stimulation signal. And there's a huge difference between the signal levels in many applications. And so I won't go into details on this, but this is something that we realized at the University of Washington. It was actually tested in a monkey lab. It's got some interesting circuit tricks that were utilized in the stimulation electronics. This has 4 stimulation centers and 64 recording channels that are time multiplexed. And this was implemented in a 65 nanometer CMOS process. Now we'll get into the technical details really in the wireless area, what the challenges are, but I'll just say that what's interesting about this problem to me is that the amount of suppression that you need of the stimulus artifact, when you work out the numbers, it actually is very similar to what you need in a wireless system, north of 100 dB. The big stark differences between, say, this application and wireless is that it's low frequency, so it's all audio type bandwidth, so you have that as an advantage. And distortion of the electronics itself isn't such a major issue, but the low frequency issue is a major advantage because we can utilize digital techniques to synthesize, say, artifact cancellation signals. The one big challenge about this, as compared to wireless and other applications, is that the impedance looking into the recording electronics sensing electronics is very high, the electrode impedance. And that makes it challenging from a noise perspective to inject the anti-signal or the inverse signal. So, another theme that you'll see throughout this talk is, how do you adapt these systems? And so this was a paper that we had at SCIRC a few years ago. And the artifact adaptation was done using, just digital FIR, and it was integrated on the chip, and there was an algorithm that was a straightforward LMS, and to save power, we actually time cycled through the multiple channels used from each stimulation site to all 64 of the recording sites, and those were stored through the adaptation. Now here, power is everything, but adaptation time, not so much. Why? Because the channel between the stimulus site and the recording site is really not time varying. It's slowly time varying, like literally months it'll vary as the impedance of the electrodes increase through corrosion after we implant in the body. And here we see the actual adaptation of this system. And then this was tested in a monkey, and you see the recording output with no artifact, they call it stimulus artifacts, is there self-interference in that community. And here you see it both before and after the artifact suppression is adapted and turned on. So it's quite a remarkable difference, and I think it's a pretty interesting application. This is another area that I find interesting and we're trying to get into. I don't have any work, but there's some nice work that came out of here. I picked this one because it came out of Delft in Holland and EPFL in Switzerland, and this is the control of quantum, spin qubits in this particular case. And each of these quantum dots or bits or whatever you call them, there's different types, and they have different types of electronics, but mostly, we run these at very low temperature as much as possible for most of the qubits that I've seen. That's one thing, and then we read and write to it basically using a radio. So we're driving a transmission line that if we want to sense what the qubit state is, we stimulate this, and then we listen at the same time. So again, this is an application where you have to basically excite and listen on very close frequencies simultaneously at the same time. And you'll see actually, mitigation techniques in here to increase the isolation. This was actually an off-chip isolator, and some of the folks, I think Eduardo Charbon, I don't know if he's here, have actually integrated that circulator onto the chip itself. So it's very interesting. So again, I could go on and on with different type of applications that are out there, but to me it's quite interesting. Radar, again, one that has been around for a while. You have a reference signal while you're sensing, neural interfaces, sonar, cable modems. They actually use full duplex on each channel in a very well-controlled environment. And this is not research. This is a product that you can buy right now, right? So this is something that you can use. Emerging, wireline actually is pretty interesting. So NVIDIA came out with an interesting paper a year or two ago at ISSCC where they're trying to read and write on the same channel. And that is also difficult. So in the imaging community, we talked about quantum interfaces. In the imaging community, this is also a problem in MNR and positron emission tomography imaging, which we have also done some work. And of course, what we're here to talk about today, which is really next generation wireless systems. So this could be car radar, this could be 5 and 6G applications. I actually think Wi-Fi and Bluetooth, you could lump them in there. They've always had this problem of self-interference in some sense, dealing it through TDD. So what I'd like to do is just, a little bit of the motivation. Let's get into, some interesting, topics associated with this problem. And then we'll look at some examples. Okay, so what's the issue here? We increasingly more and more devices that per person, more and more radios, more and more radio applications, and the opportunity to interfere with each other is increasing. Now again, the reason why I like this self-interference problem, because it's the extreme case of all these interference issues. Why? Because we're generating the signal. There's no opportunity for filtering in some sense. Because there's no frequency specificity on the one hand, And also the signal is extremely strong, while in some cases we're trying to receive a very weak signal. So if we can solve that problem, I think there's a lot of interesting things you can take from that area, or the outcome of that research, and apply it to the broader case of just broadband interference. And of course, in the sort of the full duplex community, there's sort of this theory that you can actually increase, the overall win that we would get from spectral efficiency is 2x, which we'll talk about in a moment, on the high side. But there are these networking papers out there that say you can actually increase the data rates and drop the latency by as much as 10x. And again, that's critical for these future applications in 6G, where really latency is everything, right? With the whole edge computing network that we have out there and all the different devices and autonomous vehicles, et cetera, latency is critical. And really, there's going to be two overlying things: latency and security throughout the network. And again, that kind of points to another area of interest, which is really applying AI to a lot of these problems, machine learning problems. So let's just quickly go through really what are some of the challenges in this area, and then we'll look at some recent examples. And then I'd like to talk about really the optimization of these type of front ends using some AI. It's really early in this community. We've done a little bit of work. We just had a paper at ESCERC a couple of weeks ago in Bruges on this topic. And we could only find 2 other papers that are really more from the digital community, not from a community like this of wireless front-end people, analog front-end people. All right, so what's the issue? I think most of the people in this room sort of understand, the topic is that, you have full frequency division duplexing, which is very common throughout, Asia, Europe, and North America, where we simultaneously transmit and receive on 2 different channels and different power levels, output power levels. And of course, the sensitivity of the receiver, can be extremely low if we're far from the base station. So this crazy idea that, sort of really came, to light, I suppose, well, from the military community has been looking at this problem for a good 60 years, right? But in the academic community, we got real interest about 10 years ago. Columbia, I think Delft, others started looking at this problem as well as our group. Of this idea of overlaying the 2 channels, all right on top of each other, and thus increasing the spectral efficiency by a factor of 2x. So the obvious problem that you have is this transmit signal, both in time and frequency, is interfering with the potential receiver. Okay, so sort of the high-level challenges. How do we actually do this? We're going to add something between the transmitter and the receiver to increase the isolation somehow. But actually, I should say mitigate the self-interference. But the isolation, again, is decreasing through more integration and in more advanced technologies. And so we want to do something between the transmitter and the receiver. And what we have to worry about is the noise, the linearity, and it looks like something got dropped there, the bandwidth of whatever technique that we're using to somehow remove this large signal that's very close physically from the receiver. All right, so some other challenges, at least from the analog electronics perspective, is longer delayed reflections. Those are more challenging. We want wider cancellation bandwidth. And of course, this is really something the community, I think, is really starting to focus on now, the adaptation of these systems. Because unlike the neural interface, this one is highly dynamic. All right, so the interference is changing as I rotate my device and I walk around with it. The impedance, the antenna is changing. The interference profile is changing, et cetera. So we, kind of like to classify the type of interference that we have. There's really direct coupling, say, through the substrate or the chip and the board. Some reflection that's very close either at the antenna or, an ear or something like this. And then the more, problematic ones are these, longer delayed reflections that we have, which bounce off, not a building necessarily, but across the room, a large room like this. Becomes challenging because you have to synthesize that same delay, perhaps in the analog domain, to create, some cancellation signal. But For this long delayed reflection problem, you do have an advantage that, as the signal goes out and comes back, there is path loss, all right? And this is, something that we looked in our lab, and this was an SCIRC paper from a couple years ago. Is what you'll see is the, sort of the time of flight. We took these measurements in various environments, office, hallway, a big atrium like this. And what you'll see is that direct coupling coming in very strong with a short time delay. And then, as we go out, as we go further away, the amplitude of the power level is decreasing, and these environmental reflections are lower. So that actually presents a little bit of an opportunity, and that's something that we'll just discuss briefly in a moment. So again, then the challenge, is that we want to increase the bandwidth. These systems that we're talking about, in 5 and 6G, talking about hundreds of megahertz. So the electronics would need to actually track that self-interference over the entire bandwidth. And it has to track the frequency response both in phase and amplitude. And it has to be adaptive to that phase and amplitude, which is very difficult to do. All right, then the other, challenge, and this, I would say this, from a hardware perspective is probably one of the big ones. It's not so much noise of anything that you might put between the transmitter and the receiver. It's the linearity, particularly with multi-carrier systems, really becoming quite prevalent. The opportunity for those subcarriers to intermodulate with each other exists, anything that I might put between the transmitter and the receiver, and increase the noise and distortion floor of the receiver itself. So the nice thing is that there's multiple opportunities where we could actually perform this cancellation or isolation between the transmitter and the receiver, in the air interface, in the analog electronics, and in the digital back end. And some of the things that we've looked at is, over the last 8 years is exploiting those various points in the receiver between the transmitter and the receiver where we could inject cancellation signals that are the inverse or do some type of isolation technique. At the interface, you could use 2 antennas. You get, 20, potentially 25 dB of isolation. A circulator on the front end, whether off chip or integrated. And then, very commonly you'll find that somewhere between the transmitter, in our case, we'd like to go at the output of the power amplifier, which provides challenges from a linearity and noise perspective, putting something between the transmitter and the receiver as a reference signal to cancel the self-interference that's wrapping around. Now, just quick tutorial here. One of the advantages that you have in the receiver, particularly if you layer the amount of cancellation as you go down the receiver chain, is that you can increase the isolation or suppression of the self-interference as we go down the chain. And as we go down the chain, that allows us to perform increasingly complex methods of performing this cancellation. For example, if we sort of look at the leakage as it wraps around to the front end, if we do a crude cancellation up front, we can actually lower the undesired signal while raising amplifying the desired signal going through the LNA. Now, the desired signal is higher and the leakage signal is lower, so that's more forgiving from a noise and both noise and linearity perspective for this, say, the second canceller. And then in some of our work, we've actually down-converted in the analog domain and injected the inverse signal, and actually not shown here, we've actually used an ADC and gone into the digital domain, which we'll discuss in a moment. Now, the interesting thing about this is, the trade-off, the classic link budget for a radio receiver, distributing the gain is, if you're talking about noise, you want as much gain towards the front end as possible to overcome the noise at the back end, but then that trades off with linearity, all right? So that hurts the linearity. And so if you're really after linearity, you're going to distribute more of the gain towards the back end if you're trying to improve the linearity of the receiver. What's interesting about these cancellers is both noise and linearity, it's an advantage. It's more relaxed as you go towards the back end. Again, because this leakage signal is decreasing and you're increasing this received signal. So you can do something actually quite complicated in the back end and maybe just do some crude type of cancellation on the front end to reduce, just to ensure that the receiver doesn't saturate or really cause, large linearity problems. And so we actually had a couple papers. This was an ISSCC 2017, and we had a JSSC paper that followed up. This actually included two cancellors. One was right at the front end, and then we down converted using the same synthesizer, the output of the PA, and went into this really, actually a very complicated at baseband DC, or direct conversion, complicated IQ filter, complex filter that had, I think, up to, I can't remember, I believe it was up to 15 taps. And that was done in the analog domain, and then that's how the suppression was performed. Later, actually, a couple years ago at SCirc, we had something, quite a bit more complex. We had what is sort of like a circulator, an electrical balance duplexer. It's not a circulator, but it provides isolation between the transmitter and the receiver and the antenna, kind of in a similar way to a circulator, although it doesn't work nearly as well as a circulator. This was integrated on chip. And then we had both a pre and post canceller at the before and after the LNA. And then again, we had this down conversion path, and we went into the digital domain with an ADC. And here we could synthesize a really long delay tap, digital FIR, and it could be very programmable to track multiple reflections. And so that was actually pretty interesting to us because, again, it sort of solved this problem of, long delay spread self-interference reflections. So each of these has a separate role, as I sort of explained in the prior slide. What we're doing here is more crude to lower the strength of the self-interference. Well, this is really a complex filter in the digital domain that's tracking long delayed cancellation. Long-delayed self-interference. Now, you might ask, well, this has an ADC and the power and the area. Yes, that is an issue. But in the reference path, we know the amplitude of that signal, right? We have control of that. And again, the reflections we're talking about, these really long-delayed ones, they are significantly reduced in amplitude. And so what I'm talking about is more than 3 nanoseconds. And the amplitude is such that it can pretty easily pass through a conventional ADC. So again, short delayed reflections, strong in magnitude, longer delayed reflections in this mixed signal solution here. And so just as an example, this was a chip. I can't, time forbids me to going into all the details, but it includes a PA, the receiver, the cancellation paths, the two complex, actually the two FIR, true time delay analog filters, the receiver here. This included the phase lock loop, and this was actually another cancellation circuit. Now this sort of leads to now, the next thing that I want to transition to, which is really how did we test this, and what do I think is really the challenge going forward. I think there's been a lot of great work from many universities and companies around the world on solving the hardware problem, the linearity, the bandwidth, the noise performance of these type of circuits that we realize in the front end. But now it's about, again, it's a point solution. I get everything, I adapt it in the lab. Everything on our chips is all digitally controlled. Everything in the analog domain, the filter tap values, even though they're analog, the delay values, even though they're, we're talking about an analog delay, all of that is controlled with a digital bus. So we have, 5, 6, 7 bits of resolution in some cases. So what's really the challenge is how do you adapt this in nearly real time, right? So you can imagine as you're moving around quite quickly, all of those filters that are optimized for a 1 setting to get 100 dB of cancellation, I rotate the radio or I move around, how do I track that? And so what, how we did the testing in the lab, here's our chip, and we use a Xilinx RF SoC FPGA, and all of our algorithms are implemented on this device here. And initially for this chip here, it's really crude. It's using some sort of crude, greedy algorithm, a search algorithm of some sort, and it takes a long time, prohibitively long, to adapt this type of system. Anyway, I just throw this as a comparison to other work. The other thing that, again, time forbids a little bit is the linearity was enhanced through an adaptation technique, which actually I'm going to talk a little bit more in just a second here. So now, I'd really like to, this issue of adaptation, and this was the paper that we just delivered at SCIRC a couple weeks ago. And the issue is, if we sort of look at this in time, the frequency response and the orientation of the radio as a function of time, right? The radio is moving relative to potential objects that you interfere with, and the orientation is changing as well. So it stands to reason that the frequency response, the amplitude, the phase, etc., all of that are changing, and they're changing across the channel itself. So that's actually hard to track, all right? And I think it makes so this is an example of why I think this is such a great problem to work on, even if you don't believe in all this stuff, is that I think if you really think of it more as a radio calibration problem or optimization problem, you sort of look at this in the vector space, right? We need to tune something, in this case, a filter between the transmitter and the receiver, the filter taps, the delay values, all of that, which we have control of here. But we may want to do things like calibrate the linearity of this, which we do in this particular case. Or you may want to just calibrate something in the phase noise or the noise figure, anything. Future radios, in my opinion, will have as many vectors as you can possibly implement in the front end as possible. And then you're going to want to optimize that for some target, whether it be power or it be SNR, whatever it may be. And it has to be very quick. So that's why I think this problem is interesting, is sort of stepping in that direction. Is that we want to input, and in this case we do this. We phase and the linearity, the gain and the delay spread of the filter itself are all adapted. And so, just as a comparison, I'm going to go very quickly here because I know Natalie is going to be upset if I'm late. I know Europeans are always on time. I'm an American, so sorry. I'm never on time. So there's some, other algorithms. So as I mentioned, we had our version, which was an analog true time delay filter for each of those cancelers on the very front end. A couple of papers that really use a crude adaptation algorithm called the greedy algorithm. And the big disadvantage is, there's a couple of disadvantages, both in the filter architecture. This uses real tap values, and the adaptation takes a long time. Now, people have been looking at end-path filter solutions. These are really interesting because they're highly programmable, right? People believe they're digital. But again, in this case, it's a little harder to adjust the phase delay between the filter taps. While you can adjust the entire delay spread of the whole filter, it's hard to do the tap spacing using this end-path approach. So what we actually implemented for SCIRC is a complex analog true time delay filter where we can set control the taps, but also the delay values between the taps, tune the linearity and the linearity bottleneck is in the transconductance stage itself. And so what you see is the amount of self-interference suppression for both a real filter and a complex tap, filter with equivalent taps. So both one has 5 real taps, the other one has 5 complex taps. All right, so you can see that the suppression is quite a bit lower. Now, the challenge of this guy was that the delay spread, because it's purely analog, is not particularly good. Now, again, if we talk about adaptation, great work that's been done out there, and I'll just, implementing LMS algorithm is very difficult in the analog domain because we have to tap. Somehow, if we're going to do the adaptation in the digital domain, each one of these tap values have to be converted into the digital domain. So how do you do that at the expense of doing that? But somebody at Illinois actually kept the entire adaptation in the analog domain, and that's very interesting. And as we talk about adaptation time, this is interesting because it's very rapid. Now, some issues that I may think of is the noise and the linearity of all of this purely analog LMS algorithm that they use for the adaptation. All right, and so again, this is what we do is, we did in the past is a greedy algorithm or gradient descent algorithm. Great work. well, not by us, but by others. But again, it's the convergence time. And as we move into the future, as many things are trying to adapt in real time in the radio, that becomes increasingly more challenging. This is the third solution that's been proposed, which is to do, basically for every single filter setting, take a measurement of the response, store that in a lookup table, so sort of compute offline what the response is, store that, and then call that response back. Now, one disadvantage of this is that, yes, you can get, a whole table of phase and gain and frequency response, delay spreads, et cetera, for all the different settings of the entire filter. But if there's process temperature variation, you kind of have to go back and then recalibrate everything, which is challenging, of course. So the approach that we're really looking at is, and what we published a couple of weeks ago, is really using sort of an ML-assisted approach where we really have a convolutional neural network that tries to home in on the filter settings that we have, and this is on chip here, what you see. And everything you see here was actually implemented in the form of an FPGA. This was for an US Army project. It was actually a secret project, so don't say anything. Hopefully nobody's here from the CIA to take me out or something. No, this was in the public, there was a carve out in the public domain for us. Just focusing on you'll just see the canceller, and the rest of the radio was, the front end of the radio, I had no idea what it was. It was a pretty interesting project to work on. And then this was all done in the digital domain. So what we do, again, we have all this control. It's a complex analog FIR filter. We have a programmable analog delay line to enhance the delay spread up to 3 nanoseconds. That's tunable, and that takes quite a bit of area, but it has the advantage the linearity is very good, say, compared to like N-path filters, for example. This is purely passive. So the idea is that, initially what we do is some machine learning algorithm to quickly converge on, tap values that are close, and then clean up the rest of and get a deeper cancellation and a more a matched response to the self-interference by using something like a greedy algorithm or gradient descent to fine-tune things a little bit further. So this was the analog tap delay line, and then this is the complex FIR filter. We could tap off each one of these points. The switch is one bottleneck in the linearity picture from the input to the output. Of course, the PA is sitting here, so quite a bit of power being delivered there. And the switches, we also tune the tap delay values and the GM stages for each stage. So the switch linearity here is actually quite important. And then this was a linearity tuning algorithm that we use, again, controlled in the digital domain, and we can optimize it. So what we did in both our lab and in the atrium is we took thousands of samples with different antenna orientations, and stored those, and some learning was done offline. And then we go into a convolutional neural network by preloading up to 250 channels, I think are the response, or kernels as they call them in the AI community. And we convolve that with what we actually receive, and we use all of the error signals from those convolutions, and then that's put into a CNN. In the interest of time, I'm going to actually skip through these details here. It's more from the computing community. And then one challenge I'll just mention is, you can ideally synthesize some algorithm in Python or in MATLAB that you download to the FPGA, but the FPGA is, resource limited. So you have to do some things to, you're limited in terms of memory and the number of multipliers that you have, so the number of nodes that you can create and the pooling layers and all of these things that are going on. So this is the chip. It's implemented in a 40 nanometer process. You see the tap delay value here. It's quite a large chip. Again, what we were after, this was a military project. Linearity was a big deal. They didn't care about the area. And then here you see the setup. You actually see the chip. You see the chip on a daughter board, and then this is this RF SoC by Xilinx. Has a bank of high-speed both ADC and DACs. And so what you're looking at here is, that crude, very fast, rapid suppression that we get from just the CNN, and then we clean that up with a deeper cancellation of the using a greedy algorithm. And so you'd see, both before and after adaptation for a 20 and a 40 megahertz signal. This was for a Wi-Fi system. Again, the linearity tuning that we did, this actually gave us a boost of 8 dB. So we get 38 dB IP3 looking into the canceller. You might say, wow, that seems impossible. But actually the impedance, it's the output of the PA, the impedance is only 6 ohms. It's not 50 ohms. So what I might point out in sort of conclusion here is that from this work, it's really hard to compare it to other work because many people don't report their adaptation times. They just try to get it to work in the lab, and they're really focused on the front end chip and getting good measurements of the self-interference cancellation. This work I mentioned at Illinois, it's just lightning fast because it's all purely in the analog domain. But if I compare it to our own work, before and after, before it was 130 seconds to do adaptation of this type of filter, and using the CNN, we've dropped that to less, 160 milliseconds. And it's all digitally controlled. Again, compared to this one, this is purely in the analog domain. So, so what I'd like to say in summary is that I think this is a great topic from AI, circuits, architecture. If you look at it in the findings and sort of the IP that's generated can be applied to many different areas at the end of the day. All right, and not just wireless, but many other applications. So I think it's a really interesting problem, and it really takes me back to when I was a graduate student in the 90s and we were just trying to integrate the radio on chip in CMOS. That was really challenging, right? And the best synthesizer, the best ADC, the best linearity of some amplifier, all of that came into play in the 90s. And I think this particular problem, it's the same thing, and you can have better synthesizers and through research, et cetera, that apply to many applications. So the problem is on many levels. And I think with respect to this AI stuff, what I've shown is by far not the optimal solution. We don't know much about machine learning, although many people at my university do. We have a famous computer science department right next to Microsoft and Google and Amazon. I think this is just fresh territory, many opportunities to explore in the future. I'd like to thank the U.S. Army, my graduate students, Boeing, at Qualcomm, various NSF, et cetera. And then I'd also like to mention, I'm going to do this shameless plug, I'm interested in European collaborators. I'm a dual citizen from France and the US. So Dasu or Raphael or anybody, if you're here, I'm very interested in speaking with you. And so I'd like to thank you for your attention.
Thank you, Chris, for the presentation. We have time for 5-minute discussion or question from the audience. So we will have a microphone around if you want to ask some question. The floor is yours. Okay, so I will ask one. Thank you for your nice presentation, results, and architecture with a lot of building blocks and a lot of work on it. I wonder, how do you manage the temperature drift in the process, in the architecture, in the design, and the impact on the different performances?
So that's part of the adaptation algorithm. As that's varying, that's one of the variables that's varying. So as I move around, again, the orientation of the radio, the delay spread, the phase, the gain, and the process temperature and voltage variation of those components, they're all varying. And so it's comprehensively through this machine learning algorithm. The reference signal, so one of the things I did not mention, if I can go back, let's go back to, oh, here we go. So if we go back to this slide, again, I didn't have time to go into other work. There is other work using machine learning algorithms for full duplex applications, but it's strictly kept in the digital domain. So they synthesize this signal that they're trying to track in the receiver using a machine learning algorithm, using the digital portion of the transmitter as a reference. We use the analog All right, so this is our reference path. So we're capturing, the temperature and voltage and noise and nonlinearities of the transmit path. And again, we're doing the adaptation, so that's our reference path, okay? And then we're also looking at the interference signal in the receiver. And those two are being convolved all the time. All right, so as the temperature varies, as the process varies, it's just another one of these variables out of many variables, right? And I think, again, I want to emphasize, I get challenged a lot. Well, you could use LMS or you could use great signal processing experts. Yes, you can, but I think the future is what I'm trying to emphasize is that, it's not only linear things that you're trying to tune, but many nonlinear things that you may want to tune simultaneously and very fast. And which one wins in the end? Is it more traditional gradient descent algorithms or linear regression techniques, or is it something like this that applies AI and tries to track all of these variables, and not tens of variables, but thousands of variables that potentially changing and trying to track that in real time. And that I think is an interesting problem.
Yeah. Thank you very much. Yes, Patrick.
Oh. Hello. Long time no see.
Hi Chris, Patrick Reinhardt, KU Leuven. I was wondering, can you also use these techniques to kill parasitic oscillations on chip and also to kill on-chip coupling between
on-chip what?
On-chip coupling,
yeah.
and low feed-through and so on.
Yeah, I mean, again, it's sort of, I don't, so on-chip self-oscillation, that is an interesting question, actually.
Thank you.
The second one, I think the answer is yes, you can capture on-chip. It's just another coupling path, as we discussed in the front. But the on-chip oscillation one, again, I don't know. I think it's a great, again, it's untouched territory.
You were looking for collaborations. But going back to
I am looking for collaborations.
Going back to
I
the
hold
first
a French
question,
passport. I do.
Going back to the first question, so in your experiments, how much cancellation did you do off-chip? I mean, from off-chip coupling and reflections? And how much do you think were actually happening from on-chip coupling and reflections?
That's a good question. And no, we did not look at that. I try to do a breakdown of where the coupling was actually coming from. That's an interesting question, though. Yeah, I think it's something we could look at. I hadn't thought of that before. So, thank you. Opportunity for collaboration. Yes, I'm shameless.
Okay, thank you, Patrick, for the question, and thank you also, Chris, for the talk.
Thank you so much for
to move to the second plenary.
Thank you for inviting me.
And we have a gift for you. It comes from Limoges.
French?
Yes, it's a French gift.
French and fragile.
French and fragile, yes.
So let's move to our second invited talk. We are very pleased to introduce Dr. AndreiaCathelin, Technical Director of Advanced R&D Design and Technology at STMicroelectronics in France. AndreiaCathelin started her studies in electrical engineering at the Polytechnic Institute of Bucharest in Romania and obtained the Master of Science degree in 1984 from the Electronics Engineering School in Lille, France. Then in 1998, she received a PhD from Lille 1 University, France, and she joined STMicroelectronics. Dr. Cathelin has extensive expertise in RF, millimeter wave, terahertz, and ultra-low power circuit design. She has been recipient or co-recipient of several awards in international conferences, and in 2020, She received an honorary doctorate from University of Lund, Sweden. She is a very active figure in the IEEE community, being strongly involved in the organization of a number of conferences, and also is an active founding member of the IEEE ECCS Women in Circuits group. Dr. Cathelin will explore in her talk the role FD-SOI CMOS technologies will play on the Internet of Things arena, with emphasis on application fields, integration challenges, and sustainability issues. Dr. Cathelin, please, the floor is yours.
Thank you very much, Mr. Chairman. And thank you, Natalie, for the invitation to this talk. So not very easy and comfortable to speak after Professor Rudell. Okay, but I have to share with you, I might have a tiny advantage because today is my second time I'm on the stage of a plenary of a EuMIC conference. So almost 10 years ago, so the general chair of that time, Professor Crolles, who is here also from Bordeaux, so had invited me because at STMicroelectronics we were starting working for industrialization of a brand new technology worldwide, which was the 28 nanometer FD-SOI CMOS technology. So this technology is meant for ultimate energy efficiency. So we were targeting it for IoT market. But think 10 years ago, did you know exactly what was IoT? How many IoT objects did you have? So today is my honor and pleasure to present you about FD-SOI as a game changer in the IoT arena, and also as a subtitle mostly for the young scientists that are in the room here. So I want to tell you that our designs are changing the world. So the outline of my talk is the following. So I will first present you a glimpse on the IoT strategy inside my company. We will then discuss a bit about the FD-SOI technology, which is by construction energy aware. And then I will present you an IoT design example related to what we called human intranet, you will see. And this will bring me to some sustainability aspects that are very dear to me. And finally, I will conclude. And as you've already had the class by Professor Rudell, this will not be a class, okay. So let's have a look about the IoT strategy inside STMicroelectronics. So we are a French-Italian company, a multinational, and I come from the Crolles site near Grenoble. And so we have 4 major sectors of activity. So first of all, we can talk about activity around automotive, how to make driving safer, greener, and more connected. This then goes more centroid also to the people in their homes, inside the cities that they live, and even more towards the things that they are connected to. So we want to make the homes and cities smarter for a better living, for higher security, and to get more from the limited available resources that we have. And inside our houses, we have also a lot of connected things that we want them to be smarter, of course, so as I said, connected and more aware about their surroundings. And last but not least, we are also active on the pillar of the industry, inside the workplaces and factories, that we want to make them smarter, safer, and more efficient. So in order to make it to these 4 sectors, so we have 3 pillars that we consider as long-term enablers for the company. So, and you will see they are all entangled. So the first one is the smart mobility. So that is about what is inside the car. So not only this small, tiny connectivity, but also how to make the driving safer, greener, energy management of the car, and so on and so forth. Then we have a second pillar, which is power and energy, which is how to increase energy efficiency and to use renewable energy. So you see entangling with the first. And then the third one is cloud-connected autonomous things. So how can we support the proliferation of secure and connected and these autonomous devices which are enabled by Edge AI? And you can see that this one is also entangled with a smart mobility. So I would like to focus a bit more on this cloud-connected autonomous things. So you know that we are really in a big boom of this kind of market. So by next year, it's expected to have more than 20 billion IoT objects. I don't know how we can count them. I have no idea. Maybe it's 200, 2,000, I don't know. I mean, really a lot. And this market has a very strong growth these days, so more than 30% per year. And this market has to be aware about the security also that we enable in these connected objects. So we need to serve this market through three stages. So one is the cloud-connected and data-enabled services. The other one is the digital security for all data. And last but not least, the Edge AI proliferation for this. So now I've chosen a sketchy slide. So this shows you a multitude of heights. It's a very, very small subset of the IoT objects that we have around us. So you can see they come in many, many form factors for many types of applications. Nevertheless, they have all same things in common. Their needs as IoT nodes are the same. And so you can decline them by these four categories: smart things, inside the smart home, inside the smart city, and or inside the smart industry. So first of all, they have needs in terms of processing and security, and depending on the type of object. This can come from ultra low power to high performance, and of course, enabled with the needed degree of security. Then they need to be enabled with sensors and actuators, and I let you imagine all these kind of sensors and actuators that you have, and even more than that. They need to be connected, and it's either short range or very long range, up to kilometer range if needed. They need a signal conditioning and protection, and this depends on the power that they need. And also very important, they need a power and energy management, especially for those who are meant to survive very, very long time, meaning to have a very low power consumption. So these IoT objects need, in order to be economically viable, to be embedded into one chip, so systems on a chip. So at STMicroelectronics, we truly believe that the FD-SOI CMOS technology is enabling this integration path. And with this, I will pass to the second step of my presentation, where I will try to be very brief on this FD-SOI technology. People who know me, I can talk for hours on this. Okay, so this FD-SOI technology, which is by construction energy aware. So I'm talking about it generically, because at STMicroelectronics, as of today, we are dealing with two technology nodes, the 28 nanometer node and the 18 nanometer node. I will show you a bit of detail, maybe more on the 28 nanometer node as of today. So this technology, so remember, so we introduced it like 10 years ago. We were the first company worldwide to introduce such technology as being a fully depleted solution to what the market was needed, and it is a planar technology. Planar means that the transistor channel is parallel to the mechanical bulk of the substrate or of the chip. And so this technology has the particularity, I will not show on the slides because I cannot show on the two screens. So you can see that yellow thin layer, which is a ultra-thin buried oxide. So in the 28 nanometer node, it has 25 nanometers of thickness. It is placed just underneath the conduction zone of the CMOS transistors, and this insulates the front side, conduction side of the transistor with respect to the body of the transistor. This permits really a total dielectric isolation. This permits to operate on a channel that is fully depleted and no doping needed, and for analog and RF devices, it doesn't need any pocket implants. So this is really very important, and this was really a revolution when we managed to introduce it and to go towards industrialization of such a technology. And so this technology has another nice feature, which is what we call the body biasing, and I have dedicated the next slide on it. But first you have to keep in mind that it is really the dream integration technology for power and energy efficiency, for analog, and when I say analog performance, it's let's say a conglomerate analog RF millimeter wave, and is also robust for mission critical application. So, and as I said, SoC implementation. So now let's have a look on this story of the body biasing. And so, indeed, now we have access, we have full dielectric isolated access to the body of the transistor, the volume underneath of the conduction channel. And because that insulation layer, the yellow layer, is very thin, by applying a voltage on that volume, we can modulate, we can change on the fly the threshold voltage of the transistor, meaning that in one single hardware transistor, when it gets out of the fab, you, as a designer, you can implement whatever transistor you want with whatever threshold voltage you want. And this is really a very powerful knob, especially that the voltage range of variation of this body biasing is very wide. For example, in the 28 technology, it's like modulus of 3 volts. So you can change your VT by more than 100%. And this is really very powerful and has been implemented in many products for doing several things. First of all, you can boost your performance on the fly, or you can reduce your power consumption for the given performance requirement you have on the fly as well. You can also do process compensation by reducing the margins that are regularly taken by the designers in order to fulfill the industrial specs. And we have it with a seamless inclusion in the EDA flow. So you can see that through this body bias leverage, we made this technology extremely energy efficient. And now this brings me to the next step of the presentation, where I will give you an example of an IoT solution in the 28 nanometer node, a project called the Human Intranet. So this is a collaborative project that I have been leading in collaboration with IEMN in Lille and with BWRC lab at UC Berkeley. So the idea is the following, is what about having a human which has a large network of IoT nodes on him, on her, and these nodes are sensors and actuators that are either sensing, like for example, your sweat, your movement, whatever, or they are actuating. Suppose you have a paralyzed muscle that needs to be actuated, or you are amputee, you have a prosthesis and you want to actuate it. So you have these sensors all on your body, so they are small IoTs, but they need to talk to each other on your body because the network is yours. The network is not in the cloud, whatever, is your network, okay? So these nodes, IoT nodes, so they have this sensing actuation feature. They might need some local computing with a bit of AI and a bit of data processing, really very low power, and they need to be interconnected together. So through a network, they have to talk to each other, and eventually they have to talk to a mother node that might transmit data to a mobile phone. So remember, you want to have a multitude of them on your body, and you want them extremely low power and to last very long. And I will demonstrate you here how we can optimize such a system on all the layers of the system. Not only when you design your circuit, but from the very beginning. So now let's have a look of the kind of sensors or actuators that we need to serve. So we can group them in two categories. There are those that require low data rate, like temperature sensor, chemical sweat sensor, biometric impedance, and so on and so forth. And there are some others that require higher data rate, like, for example, motion sensors or neural recording. So this means that the network that we are creating has to be a bit specialized. And we specialize, but I mean, if you specialize it too much, then it will take you too much computing to talk to it. So how did we specialize it? So we have created two types of nodes. We have the hubs in blue and the leaves in gray stars. So the hubs are interconnected through a mesh network, and the leaves are connected in a star network with respect to a hub. So for example, if you imagine, so you need a prosthetic arm, you will have a central hub, and you will have leaves that control all the fingers. So this enables to optimize this network at so the very high level system in terms of energy efficiency. As well, the hubs can concentrate the data from the several small leaves that they are talking to. And the leaves, they don't need to talk to all the network, they will talk only to their small hub that they are connected to. So we have created a system like this, and we have also elaborated the MAC layer that serves it, so you can see there the reference. And so now we are getting a bit lower on the system level layer, and let's see how we can optimize even more the energy efficiency and be opportunistic related to the application. So remember that the application is dedicated to the human body. So you want it to a human body, a living person, okay? So in communication systems, so there is something that so I don't know, whatever transceiver you do, you have a block, a system that consumes half of your power. That one is the frequency generation unit, okay? You can have it PLL, whatever. That really consumes a lot. So how can you get rid of that? So what we did, so we've been opportunistic with respect to the fact that it was on the human body, and the human body had a clock. And when it doesn't have a clock anymore, we don't, I mean, okay. So we are using the heartbeat as an electrical signal and stimulus in order to synchronize the network. And we have developed this protocol by taking into account the variations in the heartbeat, the discrepancies between the flux going down or going up of the body, starting from the heart, in order to serve this. So this is one system-level optimization, which is opportunistic. The second one is, how do the nodes talk to each other? So the first idea was to use Bluetooth Low Energy. Everybody uses Bluetooth Low Energy. But do you see yourself with small 2.4 gigahertz antennas on you to make them talk to each other? No, first. And secondly, do you want that your personal private data is sent out electrically in a wireless domain around you? Do you want to get hacked by your closest neighbor? No. So we found another way of communication which is even more energy efficient, and that is, again, opportunistic from the human body, that is called capacitive body-coupled communication. So this is a communication which is standardized by IEEE and ETSI, whatever, and it is through the upper skin of your layer of your skin. It has a layer, so the electric levels are really low, so we respected that, and we studied and we defined that the best optimized in terms of energy was at around 450 megahertz. This also has the advantage that it has privacy, because the communication is on a channel that is your body, and that is by definition secured. So you see, we've taken two opportunities of things that existed in nature in order to make even low power this network. And now let's go a bit to the silicon implementation. So here we used the 28 nanometer FD-SOI CMOS. Here I give you an example of the transmitter that we have implemented. So this will be my only schematic for today. Okay. So, so you can see the references here. So this was a paper that had the best paper award at RFIC some years ago. And so what we do, so we use FD-SOI and we use all the advantages related to body biasing. So how we do it? So we have an unlocked small frequency generation, which is done by that ring oscillator running at 90 megahertz, which is controlled by the body biasing. It's a 5-stage ring oscillator. It generates, so 5 signals dephased. Through these 5 signals and an edge combiner, we do a multiply by 4 in frequency, by 5, sorry, and we also creating that ultra-wideband shape. So by the way, we have chosen ultra-wideband modulation because that's the most energy efficient that exists as of today. By the way, do you know your heartbeat, what kind of modulation does it use? It's ultra-wideband, it's the same. Okay, so that's the most energy efficient. Okay, and then we amplify the signal by switch capacitor power amplifier. So all in one, this looks RF, but in fact it's a CMOS inverter-based design, operated at half of the VDD. So this is a technology that also is very performant at ultra-low VDD,